In October 2022, a brilliant flash pierced the cosmos, brighter and more intense than anything human civilization had ever seen. And that's not an exaggeration. The strength of the blast blinded our gamma ray detectors the world over and unleashed more energy in a matter of seconds than our sun will emit over its entire 9 billion year lifespan. Over the 18 months that followed, it became the most widely studied gamma ray burst in history, creatively dubbed the B.O.A.T for the brightest of all time. As researchers began to decipher its cause, their findings unraveled one mystery after another. Scientists have been cataloguing gamma ray bursts for decades, but this one was closer, brighter, and unexplainably devoid of some key signatures you'd expect to see. It also raises some far-reaching questions about our standard model, the possibility of a dark matter particle, and how heavy elements like gold are made. I'm Alex McColgan, and you're listening to the Astrum podcast. Join me today as we dive into the mystery of the biggest and brightest gamma ray burst of all time. What caused such a colossal explosion? How is it different from other gamma ray bursts before it? And what can it teach us about our understanding of the universe and the particles that constitute it? Gamma ray bursts are brief, intense flashes of high-energy gamma radiation lasting from milliseconds to several minutes. The first of its kind was detected in 1967, when American satellites designed for detecting covert Soviet nuclear testing picked up an unusual pattern of electromagnetic energy. Since then, gamma ray bursts have been of tremendous interest to the cosmological community, as they allow scientists to study states of matter and physics that are not reproducible on Earth. Essentially, they provide researchers with a glimpse of how stars are formed and evolve across the whole timeline of the universe. There are two different kinds of gamma ray bursts. Short gamma ray bursts last less than 2 seconds and are attributed to either the collision of two neutron stars or the merger of a neutron star and a black hole. They can be followed by a kilonova, an emission of bright light resulting from the radioactive decay of chemical elements. This decay creates even heavier elements, an important feature of novae which we'll discuss more later. Anything lasting longer than 2 seconds is classed as a long gamma ray burst. These are thought to be caused by the explosive deaths of massive stars and their subsequent supernovae. The collapsed core may form either a neutron star or a black hole. These typically occur close to the edges of the observable universe because they are characteristic of low metallicity stars which formed when there were less heavy elements around. When we see one of these, we are witnessing events from billions of years ago. In the case of both long and short gamma ray bursts, the newly formed black hole blasts out jets in opposing directions, containing particles accelerated close to the speed of light. When these particles interact with surrounding matter, they emit the gamma rays we detect. So, what made the B.O.A.T so special? Let's start by analyzing some of its key characteristics. Firstly, the B.O.A.T lasted 10 whole minutes and was detectable for 10 hours after the fact. It occurred in the Sagitta constellation, only 2 billion light years away, which is much closer than other gamma ray bursts we've detected until now. In fact, such a bright explosion so close to Earth is thought to be a 1 in 10,000 year event, meaning the last time one happened, humans had barely started farming. As is the case with other long gamma ray bursts, we know a collapsing and exploding star was behind it. But this is where things start to get fuzzy. A supernova alone isn't enough to explain the magnitude of the gamma rays emitted. The B.O.A.T was a whopping 70 times stronger than any other gamma ray burst detected. Initially, the theory was that this must be the supernova of a ginormous star, the likes of which we rarely see. However, upon closer inspection of the afterglow, scientists found that the supernova behind the B.O.A.T was shockingly ordinary. To get a clearer picture, astronomers pointed the James Webb Space Telescope in the B.O.A.T's direction. Webb's near-infrared spectrograph revealed that the supernova behind the B.O.A.T was actually pretty average. it wasn't nearly as bright as you'd expect given the gamma ray burst that accompanied it. So what could have caused such a flash? One idea is that we simply perceive the flash as bigger and brighter because of Earth's relative position to the blast. Imagine a flashlight shining in the dark, diffuse and soft. It lights the path 1 to 2 meters ahead of you. Now, imagine capturing all that light and focusing it into a singular laser beam. It wouldn't illuminate the path as widely, but it would reach hundreds of meters into the distance. And if Earth was in the direct path of that laser, it would register a super bright reading. That doesn't mean the laser released more energy than the flashlight, it just means the way it was concentrated and then detected resulted in a higher reading. The same concept can be applied to these gamma ray bursts. If a massive star is spinning super fast when it collapses, then the shape and structure of the near light speed jets it emits will be more narrow and focused, and therefore brighter. In fact, the jets seen from the boat are some of the narrowest we've ever seen. But not only were these particle jets brighter than expected, scientists also detected way more of them going faster than expected. They traveled with such fervor that after 2 billion years traversing the cosmos, they arrived here and momentarily disrupted the Earth's atmosphere. Sitting just 50 to 1,000 kilometers above the surface of our planet, Earth's ionosphere is rich in electrically charged particles. When the boat struck, it left a mark comparable to that of a major solar flare, pushing the ionosphere down into lower altitudes. If photons from an explosion 2 billion light years away can have this kind of effect on our planet, I don't really want to think about what happens if something like that in our neighborhood explodes. The large high-altitude air shower observatory in Daocheng County, China, managed to capture data on tens of thousands of photons over the course of the initial blast and into the afterglow. This is a quantity unlike anything seen before in gamma-ray astronomy. In fact, it's so far out of pocket that some astrophysicists think that they might be pointing towards something missing from our models. According to our current understanding, it's very unlikely these super high energy photons are traveling for 2 billion years. Cosmic microwave background radiation, interactions with intergalactic dust, or redshifting caused by the expansion of the universe are all factors that can interfere with a photon's trajectory. One hypothesis put forward is that photons convert themselves into a hypothetical particle called an axion, and then convert back into gamma rays upon reaching our galaxy's magnetic field. Axions are thought to be an ultralight particle responsible for dark matter. Their existence is currently purely hypothetical. We have no evidence for them, and even if we did, they would lie outside the standard model of particle physics. We don't have time to dive into detail in today's podcast, but I might take a deeper look at them in a future episode. Okay, so far we've established that B.O.A.T was caused by a massive star collapsing and turning into a black hole, which incidentally is known as a collapsar. Aside from generating a long gamma-ray burst, collapsars are also known for generating something else. Gold. Wait, how is gold connected to gamma rays? Good question. To understand that, let's take a minute to discuss how elements are made. The core of a star is a super high pressure environment, some 200 billion times higher than the atmospheric pressure on Earth. In these conditions, nuclear fusion reactions create heavier elements out of lighter ones. For example, one helium atom comes from fusing 4 hydrogen atoms together. Elements 2 through 26 on the periodic table, that's helium to iron, are made this way, a process known as stellar nucleosynthesis. However, once you get to iron, it isn't energetically favorable to continue making bigger and bigger elements this way. So how do we account for the rest of the periodic table? Where do these heavier elements like gold come from? At the moment, we know 2 different ways these elements are formed. The first was recently confirmed by the James Webb Space Telescope. When 2 ultra-dense neutron stars collide, they emit an immense amount of neutron particles. Surrounding material captures these neutrons, making their atoms temporarily unstable. In order to stabilize, the neutrons undergo radioactive decay into protons, creating new, heavier elements. This process is known as rapid neutron capture, or R-process nucleosynthesis. Some calculations suggest one neutron star collision can produce up to 3 Earth masses worth of heavy elements. However, this explanation alone isn't sufficient to account for all the heavy elements in the universe. Neutron star collisions are rare and take a long time to happen, in the order of billions of years. On top of that, observations of very old stars show that heavy elements were already present in parts of the universe well before most binary neutron stars would have had a chance to collide. So how do you explain that? There must be another source of heavy elements in the cosmos. Which brings us back to our B.O.A.T. There's another theory that collapsars like the B.O.A.T could be another source of R-process nucleosynthesis. In their dying stages, massive stars like the one that caused the B.O.A.T are surrounded by layers of exploding gas. These explosions leave disks of matter swirling around the resulting infant black hole. As the black hole begins devouring the surrounding material, it can only ingest so much at a time. What it cannot manage is swept away in a neutron-dense wind. Here, the same R-process nucleosynthesis occurs, forming heavier elements like gold, silver, and platinum. This seems promising, but unfortunately, even factoring in these kinds of supernovae isn't enough to account for the abundance of gold in the universe. To make matters worse, analysis of the B.O.A.T spectrum didn't show any traces of heavy elements, raising questions about the validity of this collapsar gold-making theory. Some scientists suggest the B.O.A.T's host galaxy might have something to do with the lack of heavy elements in the explosion. Upon modeling the host galaxy spectrum, researchers discovered it has the lowest metallicity of all previous host galaxies where gamma-ray bursts were detected. In other words, maybe the environment didn't have the right building blocks to make heavier elements. How do we know how much gold should be out there in the first place? How do scientists predict something like the relative abundance of elements in the universe? There are two main methods of calculating this: the spectroscopy of stellar photospheres and meteorite analysis. By analyzing the absorption lines in the spectra of stars, astronomers can determine the relative abundances of elements in the photosphere of those stars. The composition of meteorites, remnants of an early solar system, are analyzed in parallel to determine the relative abundances of elements. Meteorites are especially useful for measuring the abundances of volatile elements like hydrogen, helium, and noble gases that are unrepresented in stellar photospheres. The results of both of these methods are usually congruent, indicating we're probably doing something right. But this is physics, so of course nothing is so cut and dry. One famous exception to this rule is lithium. According to the standard Big Bang nucleosynthesis theory, the early universe should have produced about 3 times more lithium-7 than is currently observed. The plot thickens when we consider its isotope, lithium-6, where we observe 1,000 times more than our predictions can account for. This discrepancy is known as the lithium problem and remains unsolved, presenting a significant challenge to the standard cosmological model. It highlights the importance of understanding the processes that shape the relative abundances of elements in the universe, and suggests that our current understanding of nucleosynthesis might be incomplete. Just because B.O.A.T didn't yield gold as expected doesn't mean we should discard these kinds of extreme gamma-ray bursts as places where heavy elements could be made. Observations of nearby stars have provided strong evidence for an early R process that enriched the universe with heavy elements. But the B.O.A.T findings cannot be ignored, as they suggest there may be alternative, currently unknown processes responsible for this elemental enrichment of our cosmos. The results may call into question our entire model of understanding regarding collapsars and their role in creating heavy elements. This discovery is much bigger than just the B.O.A.T or gamma rays. It's about the literal building blocks of our universe as we know it. Where do our different atoms come from? And why do they exist in the proportions they do? How much of our model is accurate and how much is missing? What role does dark matter play in all of this? We need more time and research before we know for sure, but the B.O.A.T is a great example of how new findings keep our understanding of physics ever evolving, just like the universe itself. Well, that's all we have time for today. I hope you've enjoyed listening to this podcast on B.O.A.T. If you've enjoyed what you've heard, please feel free to follow us for more podcasts on other fascinating space topics. But for now, I'm Alex McColgan, and this has been Astrum. All the best, and see you next time.